One of the cool things that you can do with the Catmull-Rom curve is generate an offset curve. Let me show you what this looks like. Here's the Catmull-Rom curve made up out of a bunch of control points, and as usual I can grab these things and pull them around and the curve comes along for the ride. In this sketch I can draw the offset curves. Here's the outer offset curve, and here's the inner. And you can see that they're like the edges of a road given the center line. As I move the center line around, the offsets follow it nice and smoothly. This is the beauty of offset curves. I can even pull them in more tightly, or I can make them go further away from the curve itself. So let's take a look at how we generate these curves, because they're so useful in a lot of different circumstances. The technique relies on two ideas that we'll cover in this video: tangents and normals. Let's take a look at tangents first. Suppose that we have this curve. Let's look in particular at one point on the curve. At that point, there is a line that just grazes the curve. It just touches it at that point. The ancient Greeks sometimes called this a kissing line because it just kisses the curve. Its more modern name that comes to us from mathematics is the tangent line. We can ask processing to give us this line at any point. I've drawn the line symmetrically. Processing actually gives us just half of it. Here's how we can use tangents to create the offset curves. Here's a single closed Catmull-Rom curve that sort of looks like a whale. It's a very low resolution curve. I just have a few control points, and that's on purpose because I want to keep things simple. Here are a bunch of points on the curve. Now these are not necessarily the control points, although they could be. I just chose a bunch of points that are on the big Catmull-Rom curve. Of course, the curve itself is made up out of many smaller curve segments. Nevertheless, all of these points are on the larger Catmull-Rom curve, and we could generate them using curve point and the right section of the curve. At every one of these points, we can find the tangent. Starting from the top of the tail and coming down the right-hand side, we can start drawing the tangent lines at every one of these points. At the bottom of the tail, the tangent is almost horizontal, then the curve comes around, and working our way clockwise, we can draw the tangent line at every point. Finishing this process, we have a tangent line at every point on the curve. An important thing that we're going to see is processing doesn't actually give us these lines. It gives us these lines. The difference is most easily visible at the tip of the tail and the bottom of the tail where it joins the body. Notice that the tangent lines there are very short. In general, where the curve is bendy, the tangent line will be short. Where the curve is very flat, the tangent line will be long. This is on purpose because we can use the length of the tangent line that processing gives us to determine how bendy the curve is at any given spot. But I don't care how bendy the curve is. I want all of my tangents to have the same length. So we'll do that. We'll normalize them and scale them. And now comes the trick. I'm going to rotate each of these tangent lines by 90 degrees. These lines are called the normals to the curve at each point. Now I can just join up the outside edge of every normal. I can join up the inside edge of every normal, and I have made my offset curves. That's all there is to it. So let's see how to get the tangents out of processing. It's really easy. Suppose we have a Catmull-Rom curve. It's got 4 control points. Here's the curve, and of course, processing really only draws the part of the curve between B and C. Just like we did for curve point, I'm going to have a value called t that runs from 0 to 1. This works just like curve point. So when t is 0, I'm picking out point B. When t is 1, I'm picking out point C. Here, I'm picking out a value a little bit less than halfway, so we get a value somewhere a little less than halfway between B and C. We hand processing the 4 control points and the value of t, and it gives us back the tangent at that point. I'll call the horizontal distance from the point on the curve to the tangent point xt for x tangent, and the vertical distance from the point on the curve to the tangent point yt for y tangent. To get the values of xt and yt, we call curve tangent. Notice that there's a capital T there in the middle. Curve tangent works just like curve point. It takes the 4 x's and a value of t, and it gives us back the x component of the line from the curve point to a point on the tangent line. To get the y component, we just call curve tangent again, the very same routine. We hand it the y values of the 4 control points and the same value of t, and we get back the y value. If we choose a different value of t, we'll get back a different tangent. Each value of t picks out a different point on the line, resulting in a different tangent. The tangent always just kisses the line. I said before that the length of the tangent is related to the curviness of the curve. So let's see how that works out. Here's our curve with a point and a tangent point. I'll call the point where we're evaluating the curve, here in brown, XCYC, and I'll draw a vertical and a horizontal line through there. Those are parallel to the x and y axes. Well, I'll do the same thing through the tangent point. The distance from XC to the tangent point, that is the x tangent value we get back from curve tangent. The distance from YC to the y value of the tangent, that is what we get back from curve tangent when we hand it the y values. So to draw the tangent line, we would take the brown point, XCYC, and add to it the values we get back from the calls to curve tangent. If we want to draw the symmetrical line on the other side, we just subtract xt and yt, and we get the line on the other side. When we're evaluating the curve at a point like this, where the curve is changing slowly, xt and yt will both have large values, so we'll get back a long line. But suppose instead we evaluate a point where the curve is changing fast. Then xt and yt come back as values very near the point where we're evaluating. By the same token, if the curve is very flat at the point we're evaluating, xt and yt are going to be far away. So going back to our whale, these are the values we actually get back from curve tangent. The lines are very long where the curve is changing slowly, and they're very short where the curve is changing quickly. If we don't fix this, then when we rotate the lines, these will be the normals, and when we join them up, these will be the offset curves. Notice that the curve gets thick and thin as it goes around the whale, even with a very small number of points. Every once in a while, this is what you want, and if so, then this is great, and you can just use it. But usually we want something more like this, where the inner and outer curves usually stay about the same distance away from the center line. Of course, to get this, all we have to do is normalize the lines and scale them all to the same length. We've seen how to get the tangents. How do we get the normals? Well, I'm sure you're way ahead of me. If this is the tangent, then this is the normal. I'll label them for you so we can keep them straight. The tangent is the one that just kisses the curve. The normal is perpendicular to the curve. Of course, we know how to find this. This is just the rotate 90 trick. In this case, I'm rotating the tangent 90 degrees counterclockwise. So let's put all the pieces together. We start with the whale, and we call curve tangent twice at a whole bunch of points along the whale. That gives us back the tangent line at each of those points. We normalize the tangent lines so that they all have length 1, and then we scale them so they all have some nice big length. Here I'm making them about 20 or 40 pixels. Now we do the rotate 90 trick, and now we're done. Just join up the first vertex of every one of these normal lines, and we get one of the offset curves. Join up the other end of all the lines, and we get the other offset curve. So here's the center line with its 2 offsets. We can draw this another way by filling in the outer curve with blue and the inner curve with white. So let me show you all of this in action. Here's a Catmull-Rom curve with 6 control points. Here are the tangent lines. I'm drawing them as little lollipops, so they're symmetrical around each point where I'm evaluating them, but I'm drawing a big circle at one end. You can see where the curve is flat, the lines lie right on the curve, but where the curve is making a sharp bend, you can really see the lines. If I rotate each one of these lines around its center, I get the normals. Here, I'll turn off the tangents so we can see the normals a little bit more clearly. As before, I'm drawing these like little lollipops, so you can see one end from the other. If I move the control points around, well, the tangents follow me around, and the normals follow me around. So now it's easy. I just link up all of the normals on the inside, and all of the normals on the outside, and I've got myself the offset curves. I'm actually using a very small number of points here. So you can see as I pull this thing around, look in the upper right, we're getting an interesting artifact. Tell you what, I'll turn off the curve and I'll turn off the normals. And you can see what's happening. There's a little crossover or a little dovetail kind of a shape. That's inevitable. When you're turning a sharp corner like this, you're always going to get some weird little artifact up there. You can see that the curves are acting strangely. They seem to be flattening out. And that's because I'm not drawing very many points. Here, I'll show you the normals again. And you can see we have almost no normals in there. But by taking lots of additional points along the length of the curve, now I'm just drawing oodles and oodles and oodles of normals. If I turn them off, you can see how much smoother the curve looks. So if you want a really nice smooth curve, you want to find a tangent line at lots of points along the curve, which looks like that. And then you rotate each of those tangents, which looks like that. And when you join them up, you get the inner and outer curves. Here's an example with plenty more control points. If I take away the knots, it's easier to see that we have a nice center line and a pair of nice smooth curves that run all the way around it. I'll turn the knots back on so you can see if I drag these things around, the inner and outer offset curves move with me. Offset curves are great for all kinds of effects. You might want to have a bunch of geese flying in formation. So the front goose has a flight that's determined by some curve, and the other geese are flying along offset curves, parallel to the front goose. Or, of course, you could use this to draw a road. Your center line is all you need to work with, and that defines where the road goes. And then you can have the computer automatically draw the road itself and the curbs at both sides of the road. Here's another example. I'll turn off the knots, and you can see what happens when we bring the offsets in really close to the curve, basically making a nice thick curve. Or we can move the offsets far away and make a big fat party balloon of a curve.